Yeah. So welcome everybody then, and let's start with the first talk, who is given by Giulia Giordano from Trento, and she's basically in, I may say, control community, but does something very interesting about what a network can do dynamically based only on network structural considerations. So please, yes, we're looking forward.
Thank you very much, Nicola, for the introduction, and thanks a lot to all the organizers of this seminar series for the very kind invitation. Well, it's a pleasure to be here with you and share some research I'm very passionate about, indeed, which revolves around the astonishing robustness that we encounter in nature and some particular qualitative behaviors that are guaranteed just by the interconnection topology and the structure, the essence of a dynamical network. Natural systems across biology, ecology, epidemiology also can be seen as nonlinear dynamical networks, namely nonlinear dynamical systems composed of several subsystems with nonlinear local dynamics that are interconnected according to an ensemble of local interactions with a precise network topology at various levels of complexity. So the interplay between the local dynamics at the nodes and the local interactions associated with the arcs gives rise to interesting emerging global behaviors. And well, the underlying network structure of these systems indeed captures the interaction topology along with qualitative features. And it is independent of specific functional expressions in the dynamics or specific parameter values associated with the nodes and with the arcs. So dynamical systems and control theory, together with graph theory, can capture the underlying structure of the problem, which we can then exploit to analyze the system dynamics and understand what we can expect from the system behavior, or to enforce with a control mindset to enforce a desired behavior. But why are we particularly interested in the structure of these systems, namely in the graph topology, the wiring among all the various key players in the dynamics? Well, the point is, well, why are biological networks so remarkably well behaved in spite of their huge complexity? Biological systems are often very large, extremely complex webs of interactions with myriads of activations, inhibitions, chemical reactions, and still, in spite of their huge complexity, they exhibit an extraordinary robustness that can be found at all scales, from protein interactions to gene regulatory networks, from single cells to whole organisms and species. And in spite of the huge uncertainties, perturbations, parameter variations, and environmental fluctuations that affect biological systems, still they're able to preserve some fundamental properties and some qualitative behaviors that are crucial for survival. Classic examples of biological robustness are the circadian clock, which oscillates at the same frequency across orders of magnitude of variations in the parameters, and the tumbling frequency in bacterial chemotaxis that remains unaffected by step perturbations and chemical gradients. So can we explain the robust behavior of a system exclusively based on its inherent structure, regardless of its parameter values? Well, first of all, indeed, what is a structure? We call structure the qualitative description of a whole family of systems, which is typically based on the underlying graph topology along with qualitative assumptions. And the choice of quantitative parameter values and even precise functional expressions identifies a member of this family, an element of this family. Our structural analysis aims at revealing structural properties, which are then satisfied by all the systems belonging to a family specified by a structure without resorting to numerical bounds. So these properties are exclusively based on the structure and are independent of quantitative parameter values, which are often uncertain or unknown or time-varying. A structural property is even stronger than a robust property. We say that a property is robust if it is preserved for large parameter variations, large or not so large. So for all parameter values within a certain uncertainty bounding set. A structural property is parameter free. I mean, it needs to hold for all possible physically meaningful values of the parameters. And actually assessing structural properties that hold for a whole family of systems is very challenging. How can we decouple the structure and the parameters of a system in order to perform its structural analysis? Well, the tool that we have proposed is the BDC decomposition, which enables this decoupling, and which I will introduce soon. But first of all, let's look at the class of systems that we're targeting in particular. So we will focus on indeed nonlinear dynamical networks that represent chemical and biochemical reaction networks. So we can describe these as a flow graph where the nodes represent chemical species and the arcs represent reactions that turn some species into others. These G functions are monotonically increasing because we assume that the reaction rate increases when the concentrations of the reagents in the starting nodes increase. And then we can write a dynamical system that describes how the concentrations of the various species evolve over time, and then we can study the dynamic and steady state properties of this system to gain a better understanding of its behavior. And in general, we can write the generic biochemical reaction network system as a nonlinear flow system, where this matrix S captures the stoichiometry of the chemical reaction. Vector G is a vector of functions. It stacks all the reaction rate functions, and the external influxes are represented by this vector G0. And of course, graphical descriptions like this flow graph are precious to capture the system structure, forgetting about the parameters. And also matrix S, along with qualitative features of the vector function G, embed the system structure. So I will soon show approaches to assess parameter-free properties just indeed based on this structure. So for a nonlinear system of this form with a stoichiometric matrix S and a vector G of monotonic functions, the Jacobian matrix can always be decomposed as the product of three matrices where B and C can be immediately built based on the network topology, based on the graph structure. And the diagonal matrix delta in between carries on the diagonal the absolute values of all the non-zero partial derivatives in the system. So this is the so-called local BDC decomposition, which is unique up to permutations. Of course, if you permute the order of the partial derivatives, this means permuting the order of the columns of B and the rows of C, and you have a different decomposition, but up to these permutations, it is unique. And essentially, any nonlinear system whose Jacobian matrix is a positive linear combination of rank 1 matrices admits a BDC decomposition. So this is practically always the case in chemical reaction networks and in most flow networks in general, not just in the life sciences, even also in engineering.
Sorry,
and
so these rank 1 basically are the so it comes from the fact that the stoichiometric vector or something, the network vector of one reaction. This is the rank 1 thing, which appears in the Jacobian. So one can think this basically comes from the fact that a parameter like a partial derivative enters enters in the system prescribed by a vector only, which is the vector of the incidence matrix, one could say, right?
Yeah, exactly. Yeah, it's it can also be just a column in some occasions, but indeed mostly it only appears on a single column of the Jacobian. So indeed these rank 1 matrices are associated with the columns of matrix B and the rows of matrix C. And the columns of matrix B are possibly repeated columns of the stoichiometric matrix. And the rows of matrix C are essentially telling us with respect to which variable the corresponding partial derivative has been taken. So it's indeed a way to remap, to decompose appropriately the Jacobian in order to emphasize its structure as indeed the positive combination of rank 1 matrices, where indeed these coefficients are associated with the partial derivatives in the system, actually their absolute value. And these rank 1 matrices are indeed products of one column of B and the corresponding row of C.
Yeah, okay. Thank you.
Thank you. And then, so this is the local decomposition, and then a useful integral formula allows us to bring the BDC decomposition from a local to a global level. So we can rewrite the global system dynamics in this integral form where we exploit the local decomposition of the Jacobian to plug it into the integral.
I apologize. I mean, I have looked at such equations for a few decades, but I still did not understand your obviously very basic, fundamental, and elementary BDC decomposition. Could you go back one slide, please, and explain slowly? For example, you write diagonal, and I cannot understand how only the diagonal part of that matrix depends on X, because we have off-diagonal elements and they cannot disappear by a fixed matrix C.
If you take the product, indeed, these elements which are on the diagonal on the matrix in between would spread out so that you would reconstruct the Jacobian.
So is the diagonal matrix, the diagonal of a matrix, a diagonal matrix?
The delta matrix in between is a diagonal matrix.
B
and C are not diagonal. They're not even
So
square.
in other words, off-diagonal derivatives of G do not enter the Jacobian?
No, these are all the partial derivatives. So you have all the possible partial derivatives that are stacked in a vector, and this vector is on the diagonal of this matrix delta.
So the matrix D.
I don't understand. I don't understand what you're saying.
So I think it might be useful to fetch some example, but perhaps
is the diagonal matrix a matrix of the dimension species times reactions?
No, absolutely not. I mean, the dimension of this diagonal matrix is, well, the number of non-identically zero partial derivatives in the system. So all the non-trivial partial derivatives of all the entries of vector function G. So
do we agree
well,
that
you don't know.
Do we agree that the matrix in braces is a rectangular matrix?
Which one? This one, delta?
In braces, diagonal braces.
Yeah, this is just, I mean, the notation that I mean here is that this matrix is a diagonal matrix which has on the diagonal all the possible partial derivatives of the form partial derivative of the component gk with respect to the variable x.
It is an mn cross mn matrix.
Yes. It's a
of course,
square matrix.
Of course. I did not.
Sizes all the possible partial derivatives in the system. So
very good. And you're writing as a huge matrix. Thank you very much.
Yeah, it's potentially huge indeed. It's a size that does not depend immediately on the number of species or on the number of the reaction. It's just all the possible non-trivially zero partial derivatives that you can have in the system.
Yes. Thank you very much for clarifying. This was not clear from the notation to me. Okay, thank you.
Thank you. I'm happy it's clear now.
Yes,
so
let's clear now. Thank you.
Great. So let's move on to indeed the global version, which is indeed a way to rewrite exactly the same dynamics, the same original linear dynamics as in the beginning, just in indeed exploiting this decomposition. So we can, in this integral formula, we can replace the expression of the Jacobian rewritten according to this BDC decomposition, and then the whole dynamics indeed can be rewritten in this form. So given some equilibrium x bar for the system and given the shifted variable, so x minus x bar, the global BDC decomposition indeed allows us to rewrite exactly the original nonlinear system in the shifted variable, though, without any type of approximation. So the constant matrices B and C are the very same matrices in both the local and the global BDC decomposition. They capture the system structure. The unknown parameters are isolated in this positive definite diagonal matrix delta in the local case and D here in the global case. We don't care about the values or the functional expressions in delta and in D because we are assessing structural properties. So we look for properties that hold for the whole family of systems that have the same matrices B and C and that have arbitrary positive values on the diagonal of delta or positive function on the diagonal of D. And well, what can we assess based on the BDC decomposition? One interesting property that we can assess is structurally is indeed stability. So we can check whether a family of systems is structurally stable for all possible parameter values. And well, there are many classic results to assess the stability of chemical reaction networks, regardless of parameters, only based on the system structure, typically focusing on mass action kinetics. Of course, the celebrated deficiency zero theorem is one of them. But indeed, they're typically focusing on mass action kinetics, which correspond to a specific polynomial functional form for the reaction rate functions. We have proposed a new class of polyhedral Lyapunov functions that allows us to generalize structural stability analysis to the case of generic monotonic reaction rate functions. And also the dual class of piecewise linear functions in rates have been proposed by Al-Radawi, Angeli, and Sontag. So how does it work? Based on the BDC decomposition, we can guarantee structural parameter-free stability by finding a piecewise linear or polyhedral Lyapunov function, given the graph structure, so given matrices B and C of the BDC decomposition, we can apply an algorithm that generates the unit ball of the polyhedral Lyapunov function, if any, that certifies the structural stability for the whole family of systems. So whenever we find such a function, we have the guarantee that the whole family of systems is structurally stable, regardless of parameter values, for all possible choices of the positive diagonal entries of matrix D. How does it work? Well, the idea is to absorb the nonlinear system into a linear differential inclusion, where the state-dependent matrix D becomes time-dependent, and then any trajectory of the original system is also a trajectory of the linear differential inclusion, which has richer dynamics. And so without restrictions, we can, well, rescale the entries of D between 0 and 1, and we can associate the linear differential inclusion with a discrete difference inclusion. And then a numerical algorithm starts from the diamond and iteratively expands this set according to the structural directions of growth of the system, which are contained in matrices B and C. They're associated indeed with these products, column of B, row of C. And so we expand iteratively this set according to all these structural directions of growth. And the algorithm converges to the unit ball of the polyhedral Lyapunov function that guarantees the structural stability of the system if such a function exists. If the test for structural stability fails because there is no convergence to a certain set, well, this does not prevent some individual elements of the family from being stable, but simply we cannot claim that all the members of the family, regardless of how parameter values and functional expressions are picked, will be stable. To actually ensure asymptotic structural stability and global structural stability, the key is to assess on top the structural non-singularity of matrix BDC for all possible choices of the positive definite matrix, diagonal matrix D. And this can be checked through a vertex type algorithm. So essentially, if given that the determinant here is a multi-affine function of the parameters in D, essentially it takes its minimum and its maximum value on the vertices. So if it is positive on all the vertices, or at most 0, it will be positive inside the whole hyperrectangle of the parameters. And then, if the system admits a polyhedral Lyapunov function, then there is a locally asymptotically stable equilibrium if and only if BDC is structurally non-singular. And also global asymptotic stability and convergence are ensured if and only if BDC indeed is structurally non-singular, once we know that the system admits a polyhedral Lyapunov function. Why are we particularly interested in polyhedral Lyapunov function? Well, because even in very simple examples like this one, where you have this reversible reaction between A and B, and then A and B combine to degrade, well, even in this simple example, it can be shown that the only possible structural Lyapunov function is indeed polyhedral. Other types of Lyapunov functions, such as quadratic Lyapunov functions, could certify the stability of individual systems with known parameters, but they would depend on the rates. So you need to know the rates to find the function, while indeed just polyhedral Lyapunov functions can guarantee a parameter-free approach in general. And as I mentioned, piecewise linear in rate Lyapunov functions can be seen as the dual class of functions. Yes?
Excuse me, the classical relative entropy by Feinberg, is that a polyhedral Lyapunov function?
Well, it's
I
not
don't
really,
think
because
so.
there is a logarithm, so it's a different
Yes, but
class.
it asserts global stability, yeah? I mean, I guess you're flipping transparencies very fast. I'm still one page back.
Yeah, well,
Can you show the previous slide, please? The only structural, it's, next, please. Yeah, the only structural Lyapunov function is polyhedral. I mentioned a Lyapunov function which is global, which is independent, works for all reaction constants, and you said it is not polyhedral. Is that a counterexample to your claim?
The work by Feinberg assumes a certain functional form for the reaction kinetics, so it assumes mass action kinetics.
Mass action, I see. You don't.
But here we are not assuming a functional form. So indeed, you can have other Lyapunov functions, even indeed in this. Well, first of all, this claim essentially is referring to this example. So the point is, why are we looking for polyhedral Lyapunov functions? Because even in very simple examples, you can show that the only possibility to show stability structurally is to resort to these. Other types would require other assumptions, either knowledge of not just the functional expressions, but even the parameters, as in the case of quadratic Lyapunov functions, or indeed assuming mass action kinetics, which we don't.
You only assume positivity of the derivative, of the partial derivatives.
Yeah, you just assume monotonicity, either, I mean, the sign definiteness of the derivatives, yes.
Thank you for clarifying.
But sorry, welcome. Just since we are already on this slide, so basically you have this, this example, you prove for simple example that the only structural Lyapunov function is polyhedral, but you do not know yet, and you don't even have a counterexample in general, so to say. So for that, so you don't have, you would never prove that the only structural Lyapunov function for any complicated system is polyhedral, nor you have a counterexample to this claim.
Right? Exactly.
Yeah. Okay.
Yes.
But it's a motivation.
But indeed, for instance, in many cases, like indeed, even in the simple example, if you draw the surfaces essentially of the level set, it's necessarily a polyhedron. So if you want to guarantee the stability regardless of the rates, regardless of, I mean, the reaction rate functions, their expression, their parameters, that's the only universal, let's say, way in this example. We don't have an actual, like, absolutely general proof saying for any system the only option is to resort to polyhedral, because indeed actually it depends on, for instance, indeed if you want to restrict to mass action kinetics, in many cases, I mean, indeed what you use to prove the deficiency zero theorem is entropy, which is not a polyhedral function, and it's absolutely sufficient once you make the assumption of mass action kinetics and so on. So actually it depends on the scenario where you're operating. If you want to maintain the widest possible generality in terms of not making any assumption on the functional form of the reaction rate functions, not knowing the parameters and so on, then you end up in the class of polyhedral or piecewise linear Lyapunov functions. Which is indeed, well, we are considering these functions which are polyhedral or piecewise linear in the concentrations, in the variables that we consider, which are the concentrations of chemical species. The dual class that has been proposed by Al-Radawi, Angeli, Sontag is the class of piecewise linear in rates, so functions that are piecewise linear in the reaction rate functions. And indeed, there is an interesting, and they can be seen as the dual class of each other, because they would be the piecewise linear function in my framework for the system written in reaction coordinates, essentially. And indeed, there is this interesting insight that comes from duality. Let's say we're given a chemical reaction network with stoichiometric matrix S. We call dual the system characterized by S transpose. The two systems have different size in general, so their Jacobian matrices are not the transpose of each other. It's not a trivial case. Actually, essentially the dual is somehow intuitively flipping the role of species and the role of reactions. We assume that they both have an equilibrium at 0, so we neglect the constant vector in both cases for simplicity without loss of generality. And then, well, within the stoichiometric compatibility class, possibly induced by the presence of conservation laws, the primal system is structurally locally stable if and only if the dual system is. And in both cases, we can also consider, indeed, the systems where the state variables are no longer the concentrations of the chemical species, so X and Z, but are now the reaction rates, so R, which is equal to G of X, and W, which is equal to H of Z. And also these systems in R and in W are actually the dual of each other. And so we can write the four systems, the primal and the dual, in concentration coordinates and in rate coordinates according to their global BDC decomposition. And we can adopt the BDC-based algorithm, this numerical procedure, to iteratively compute a structural polyhedral Lyapunov function, if any, for each of these systems. And indeed, we see a very nice and interesting symmetry in the architecture of these systems, also in relation to global stability assessed through Lyapunov norms. For these two pairs of systems, the pair in yellow and the pair in blue, one system admits a polyhedral Lyapunov function if and only if the other system admits a polyhedral Lyapunov function, which turns out to be the dual polyhedral norm. And this can be useful to assess the structural stability of particularly challenging architectures through the analysis of their dual structure, which then, I mean, once you certify stability on the dual, implies the global stability of the primal. Now we move on to another example of structural property for a different class of systems, which is included in the class of BDC decomposable systems, but is more narrow as a class. And we consider the role of signed loops in systems with a sign-definite Jacobian matrix. So any system with a sign-definite Jacobian matrix can be BDC decomposed, but BDC decomposable systems are a much, much wider class, which also can take into account, indeed, correlations and cross-dependency between entries, and entries do not need to be sign-definite. In any case, so let's indeed focus on sign-definite Jacobian matrices, or systems with sign-definite Jacobian matrices. We know that, according to a huge body of literature, we know that negative loops are associated with typically with stability or with persistent oscillations, and positive loops are often associated with the appearance of multiple stable equilibria. And indeed, in biology, both types of phenomena are absolutely fundamental. Oscillations are important within cells and also in heartbeat and sleep phases, circadian rhythms, seasonal changes in coat and plumages of animals, and so on. And multi-stability is crucial in cell differentiation, for instance, and in ruling cell fate, so life cycle, cell division, apoptosis. And well, we can associate a system having a sign-definite Jacobian with a graph where the nodes represent the state variables and the arcs represent the non-zero entries of the Jacobian, each with its positive or negative sign. And then we can look at the sign of all the cycles in the system in this Jacobian graph, without having to know the exact values, quantifying the strength of these interactions. So again, we are in a structural mindset. We only need to know the sign, whether the interaction is positive or negative. We don't need to have any quantitative information about its strength. And indeed, if all the cycles in the associated Jacobian graph are negative, then we have a candidate oscillator. So if the system is destabilized, if the equilibrium at which the system is resting is destabilized, the system will necessarily exhibit persistent oscillations, essentially, typically associated with a limit cycle locally. And this can also be essentially associated with a bifurcation, typically with a Hopf bifurcation, and with essentially a pair of complex eigenvalues crossing the imaginary axis from left to right. And if all the cycles in the Jacobian graph are positive, then we typically have a candidate. Well, we do have a candidate multistable system, meaning that whenever the equilibrium is destabilized, this leads to the appearance of additional equilibria and thus to multistability.
Sorry, can I interrupt?
Sure.
Just surgical. So, but if the Jacobian is how you call with fixed sign, how you said?
Yes, sign definite, like
sign definite, but this means that it's not true that it's not true that in this case you exclude automatically multistationarity with this assumption.
No, not necessarily. Indeed, if you, I mean, you just know that the Jacobian has a certain sign pattern, but it can be that multiple equilibria exist.
This does not mean that the determinant cannot change sign.
No.
Okay. So because
no, indeed, and this is actually what happens in this case, because indeed, essentially what happens if you have, in the case of a candidate multistable system, if all the cycles are positive, the only way to transition to instability essentially is through an eigenvalue crossing the imaginary axis through 0 from left to right. So essentially this means the Jacobian changing sign.
So what you mean then for sign
the determinant of the Jacobian,
sign stable Jacobian is not this. So the expression.
No, I said indeed, sign definite. I don't know whether I said sign stable. I mean sign definite. So it has a fixed sign pattern. So you know that each entry of the Jacobian must have a certain sign. And you consider the class of all systems where the Jacobian has a certain sign pattern. So entry 3, 4 is positive, entry 2, 1 is negative, and so on. So that's like the definition of your family.
Yeah, this sign stable matrices.
Oh,
like
yeah.
This,
no, we're just considering indeed sign definite.
Okay.
Yeah. Yes. Signed with a given sign pattern, essentially.
Okay, good.
But without any assumption on its stability, and indeed, that's exactly the candidate multistable system is exactly the one where indeed whenever all the cycles are positive, the only way to destabilize is essentially through the Jacobian, the determinant of the Jacobian changing sign, essentially an eigenvalue moving from being negative and real to being positive and real, so going through 0, where indeed you would have a 0, I mean a singular Jacobian.
The cycles are species reaction cycles, or the meaning of R changed? I mean, P was called X before. P was called X before, I suppose, and R is still R, or?
No, well, this is just an example here with the RNA and protein interactions. So that's these are not the same R's as so these are 4 species. The cycles are associated with the links in the Jacobian graph. So they're a cycle
and is negative means that the product of signs is negative?
Exactly. So it means that you have an odd number of negative interactions in the cycle.
And likewise for positive, I could have 2 minuses on the right.
Oh, yes, indeed. It's associated with the product, indeed, being positive. So, for instance, this could also be a double inhibition. So you could have a minus here and a minus, and still this would be a positive cycle, and you would have a candidate multistationary system. Yes. So I hope now it's clear. So let's see how we can further generalize this classification, which indeed also applies to systems resulting from the sign-definite interconnection of subsystems that are structurally stable and monotone. So, for instance, instead of having a node associated with a single variable, here we have a whole subsystem which needs to be well behaved. So let's say structurally stable and a monotone system. So essentially it can be approximated with like first order dynamics. And indeed, if we have a sign definite interconnection of subsystems of this type, well, whenever we have only negative loops, we have a candidate oscillator. Whenever we have only positive loops, we have a candidate multistable system. And even more in general, we can generalize this classification to the interconnection of subsystems that are structurally stable and have a positive impulse response. So, which is a slightly, a further generalization with respect to being monotone systems. So we can adopt a kind of divide and conquer approach to simplify things. We can recognize and aggregate these well-behaved subsystems and essentially merge them into a single node. And then the same classification holds for the aggregate system, indeed, where these subsystems are replaced by a single macro node, a single aggregate node. And actually, this classification allows us to gain some insight into some physiological mechanism. For instance, we can see in this work with a physiologist, we have shown that there are in the regulation mechanism of blood pressure and blood volume, there are two concurrent structures that are structural oscillators, and that indeed regulate blood pressure regulation, one acting through blood volume and the other one acting through vasoconstriction. And another example is the onset of the mal de débarquement syndrome that leads to essentially permanent feeling of movement after a boat or a plane trip. And the onset of this disease can be explained through the internal model principle. So the fact that if you want to reproduce a certain dynamics, you need to have the ability to, if you want to adapt to a certain dynamics, you need to have the ability to generate this dynamics within. So indeed, to adapt to oscillations when we are on a boat or when we are on a plane, we start generating internally an oscillation that is exactly opposite to the one that we are feeling, so that we cancel that. And then what happens if you have mal de débarquement is that you get off the boat or off the plane. The external disturbance is no longer active, but your internal mechanism to cancel that is still active. It takes a while to switch off. So you have this internal oscillation, which now becomes the disturbance and the source of your dizziness. So there is this presence of this structural oscillator inside us that is initially activated to cancel the external oscillations. And then what happens is that, unfortunately, there is, unfortunately, in some patients turn this mal de débarquement, which is a temporary thing, into actually mal de débarquement syndrome, which is a disease that can last for like years and years. Of permanent dizziness and inability to have equilibrium, to perform daily activities. Actually, this indeed gets triggered by the presence of an internal multi-stable system and the fact that some external disturbances and some suitable hormonal conditions can facilitate the switch from one equilibrium, which is the healthy equilibrium, to the equilibrium associated with the disease, in which essentially this oscillator becomes permanently active. And also the onset of other diseases such as fibromyalgia and amyotrophic lateral sclerosis can be explained indeed by the presence of a structural multistable, actually bistable mechanism due to a positive loop, due to the fact that indeed either there are only positive loops in the system or positive loops in terms of strength, and this of course is no longer structural reasoning, but positive loops in terms of strength are much more dominant. And then of course this situation of base stability would not be dangerous on its own if we remained at the healthy equilibrium, but there is also the presence of a bifurcation triggered by external conditions or by hormonal imbalances and so on, that triggers, unfortunately, the transition from the healthy equilibrium to the disease equilibrium as a new permanent state. And also in ecological systems, we can identify bistable systems, such as in this model of honeybee health in the presence of stressors. So we have parasites, pathogens, and toxic compounds, such as pesticides. And also in this system, we can only find positive loops in the interaction graph. So this is a candidate multi-stable system. And indeed, we have a bistability that whenever you destabilize the bee colony, leads to two extreme outcomes in terms of either complete survival of the colony or extinction. And the structural classification of candidate oscillations and oscillators and candidate multistable systems can also be exploited to design in synthetic biology systems that are guaranteed by design, indeed, to exhibit the desired behavior, even in the presence of highly uncertain environments. Indeed, we can design a biomolecular clock that is guaranteed to oscillate no matter what happens, thanks to the fact that it is built as the negative loop of two structurally stable and monotone subsystems. Or we can build a biomolecular switch that is indeed guaranteed to exhibit bistability, thanks to the fact that it is a positive loop structure involving structurally stable and monotone subsystems. And then structural oscillators can also be observed in strongly two-cooperative systems, which are characterized by a Jacobian matrix with a specific sign structure. So again, we're into the sign-definite class of systems with a specific sign structure. If you assume that all the trajectories evolve in a box containing a unique equilibrium that is unstable, and we assume that the free coefficient of the characteristic polynomial is positive, then for suitable initial conditions, the solutions of the system converge to a non-trivial attracting periodic orbit. So with respect to what we have seen before, this is not just a local oscillation result, but it is a global result. So for a whole large set of suitable initial conditions, we would converge to a limit cycle, to a non-trivial attracting periodic orbit. And biological models that exemplify this result are, for instance, the Goodwin oscillator, which indeed is strongly two-cooperative, and this result applies, guaranteeing the fact that from a whole lot of initial conditions, you have the guarantee of convergence to a limit cycle. And also the Field-Moyes model for the Belousov-Zhabotinsky reaction, which is also strongly two-cooperative up to a coordinate transformation, and also yields sustained oscillations for appropriate initial conditions, regardless of the values of the system parameters. So only based on the fact that indeed we have strong two-cooperativity, which is associated with a specific sign structure, specific sign pattern for the system Jacobian. So I'm now concluding my overview of this personal journey through systems in nature, guided by their structure and their outstanding robustness and robust properties in spite of uncertain time-varying parameters. We have seen how mathematical approaches, such as the BDC decomposition and systems and control methodologies, can give us insight into structural behaviors, allow to perform structural analysis, robustness analysis, explain robust properties of the evolution of uncertain phenomena. This can help us devise robust and optimal control approaches even. And also it would be great to, and this is the project that I'm currently working on, go beyond and integrate structural and probabilistic approaches to gain a deeper qualitative and quantitative insight. And this research direction offers several open challenges that I'm currently tackling, and I'd love to tackle more in the future. But that's for another talk. Let me thank very much all the friends and colleagues with whom I've worked on these topics. And thanks a lot again to the organizers for inviting me, and thank you all for your attention.
We can maybe, yeah, thank you very much. And sorry we interrupted a bit, so it was a bit longer, but I think it was
sorry for being over time.